Welcome back, everyone. Today we're diving into an exciting new paper about Foundation-Sec-8B-Reasoning, the first open-source native reasoning model specifically designed for cybersecurity applications. Traditional instruction-tuned language models struggle with complex security tasks that require multi-step analysis. Think about threat intelligence, vulnerability assessment, and incident response. These all need transparent reasoning chains, not just quick answers. This model, developed by Meta and Cisco's Foundation AI team, changes the game. Instead of simple question and answer formats, it uses native reasoning with think tags, showing its analytical process before providing conclusions. On screen, you can see the core challenges this model addresses: threat intelligence requiring pattern analysis, vulnerability assessment needing cascading impact evaluation, and incident response demanding verifiable reasoning for high-stakes decisions. The key message here is revolutionary. This is the first open-source model that brings native reasoning capabilities to the cybersecurity domain.
Now, let's understand how this model was trained. The researchers used a two-stage training pipeline, starting with Llama 3.1-8B-Base as their foundation. The first stage is Supervised Fine-Tuning, or SFT. This phase uses 2 million diverse exemplars covering cybersecurity, mathematics, science, and instruction-following data. The goal here is to instill native reasoning behavior, teaching the model to think before answering. The second stage is reinforcement learning, where they apply the GRPO algorithm with verifiable rewards. This stage sharpens reasoning accuracy through task-specific feedback, ensuring the model doesn't just generate plausible-sounding text, but produces correct, verifiable analysis. What makes this approach powerful is the combination. SFT builds a broad foundation and establishes the reasoning structure, while RL refines accuracy on critical tasks. The final result is Foundation-Sec-8B-Reasoning, a model built on 8 billion tokens of pre-training data, fine-tuned specifically for security reasoning. Let's look closer at the first stage, supervised fine-tuning. As you can see in the paper's Figure 2A on screen, the SFT dataset contains 2 million exemplars spread across diverse domains. Cybersecurity makes up 24.6% of the data, including CVE analysis, MITRE ATT/attack patterns, and CWE mappings. This gives the model deep knowledge of real-world vulnerabilities and attack techniques. Mathematical reasoning contributes 14.8%, which is crucial for developing robust analytical thinking. Science adds another 10.3%, while safety data comprises 8.8% to ensure responsible behavior. The remaining data includes instruction following at 15.1%, code at 8.6%, and other domains. This diverse composition is intentional. The researchers wanted a broad foundation that could generalize well while maintaining a strong security focus. The key insight here is that diverse data creates robust reasoning. By exposing the model to multiple domains, it learns transferable thinking patterns that apply across all security tasks.
Now, how exactly does SFT teach the model to reason? The answer lies in a special format using think tags. When the model receives a prompt like, "Analyze this CVE vulnerability," it doesn't jump straight to an answer. Instead, it first opens a think tag, then works through the problem step by step. You can see this process on screen. Step 1. Identify the vulnerability type and affected components. Step 2. Analyze potential exploitation paths and prerequisites. Step 3. Evaluate impact severity and recommend mitigations. Only after completing this reasoning chain does the model close the think tag and provide its final answer. This approach is called chain of thought reasoning, and it makes the model's analysis transparent and verifiable. The training uses specific hyperparameters, 3 epochs with a cosine learning schedule starting at 2 × 10⁻⁵.
These settings were carefully tuned to ensure the model learns the reasoning format without overfitting. The fundamental lesson from SFT is that the model learns to think before answering, not just pattern match to produce outputs. After SFT, the model moves to stage 2, reinforcement learning with the GRPO algorithm. GRPO stands for Group Relative Policy Optimization, and it's designed for training with verifiable rewards. Looking at Figure 2b from the paper, you can see the RL data has a different composition. Cybersecurity jumps to 38.7%, instruction following is 19.2%, and mathematics is 18.2%. This heavier security focus sharpens the model's accuracy on critical tasks. The training loop works like this. The model generates a response, the system verifies it against task-specific criteria, it receives a reward signal, and then the policy updates accordingly. This generate, verify, reward, update cycle runs repeatedly, gradually improving performance. However, RL training isn't straightforward. The researchers encountered two major challenges: reward hacking and format degradation. Reward hacking occurs when the model learns shortcuts to maximize rewards without proper reasoning. Format degradation happens when the model omits think tags to produce shorter outputs. They solved these with sample-level loss calculation and format penalty functions, which we'll explore in the next scene. Let's dive deeper into the RL challenges and how the researchers overcame them. First, reward hacking. With naive GRPO implementation, the model discovered it could output just think tag, NO, close think tag, for all prompts and still receive high rewards. Why? Because loss decreases as output length increases, so the model preferred short answers that technically passed verification. This is like a student who memorizes just the answer without understanding the material. They might pass the test, but they haven't actually learned anything useful. The solution was sample-level loss calculation. Instead of averaging losses across all tokens, they first average losses per token within each sample, then aggregate across samples. This ensures each sample contributes equally regardless of length. Second, format degradation. Without explicit format validation, the RL objective inadvertently incentivized shorter, structureless responses. The model would simply omit think tags to be more concise. The solution was adding a programmatic format penalty. This reward function validates that responses include required think tags with valid structure. Any output missing these elements receives a penalty, encouraging the model to maintain proper reasoning format. These solutions ensure robust training that produces high-quality reasoning, not gaming behavior. Now, let's look at how the model was evaluated. The researchers used 10 comprehensive cybersecurity benchmarks, which you can see in Table 1 from the paper. These benchmarks span all major cyber domains. For cyber threat intelligence, they used CTIBench-MCQA with 2,500 samples, CTIBench-RCM with 1,000 samples, and CTI Reasoning with 200 samples. These test the model's ability to analyze threats, map attack patterns, and reason about adversary behavior. For vulnerability analysis, they included CTIBench-VSP, CTIBench-ATE, and CWE prediction with 3,000 samples. These evaluate how well the model can assess, classify, and prioritize vulnerabilities. Security knowledge benchmarks include MMLU-Security with 100 samples, Cybermetric 2000 with 2,000 samples, and SecEval with 595 samples. These test fundamental security knowledge and understanding. Finally, SecEval with 1,225 samples measures security reasoning capabilities. In total, that's 10 benchmarks with over 11,680 samples, providing comprehensive coverage of cybersecurity capabilities. This extensive evaluation ensures the model's performance claims are well supported. Here are the performance results, and they're impressive. Looking at Table 2 from the paper, Foundation-Sec-8B-Reasoning demonstrates exceptional performance across cybersecurity benchmarks. On CTIBench RCM, the model achieves 75.3%, outperforming even GPT OSS 120B, which scored 68.4%. That's a significant margin, considering Foundation-Sec-8B is much smaller. For CTIBench ATE, which tests threat extraction, the RL model improved by 9.7 percentage points over the SFT checkpoint alone. This shows the value of the reinforcement learning stage. On MMLU-Security, the model scores 84.1%, demonstrating strong domain knowledge. And on SecEval, it achieves 84.8%, showing broad security reasoning capabilities. Perhaps most remarkably, Foundation-Sec-8B-Reasoning outperforms Llama 3.3 70B Instruct on multiple tasks. That's a model with 9 times more parameters. The comparison bar on screen shows 75.3% versus 71.2% on one key benchmark. This proves that focused training with the right methodology can achieve better results than simply scaling up model size. Efficiency and methodology matter as much as raw parameter count.
A common concern with specialized models is capability degradation. Does focusing on security hurt general performance? The researchers addressed this by evaluating on 10 general-purpose benchmarks. These include Alpaca-Eval 2 for human preference alignment, Big Bench Hard for complex reasoning tasks, GPQA for graduate-level knowledge, GSM-8K for grade school math, Human Eval for code synthesis, and Math for competition-level mathematics. The balance scale visualization on screen represents the key question: can we maintain both security expertise and general skills? Looking at Table 4 from the paper, the answer is a resounding yes. The model maintains strong general capabilities across all benchmarks, demonstrating that cybersecurity specialization does not compromise performance on general-purpose tasks. This is crucial for practical deployment. You want a security-focused model that can still handle diverse tasks like code analysis, mathematical reasoning, and natural language understanding. Foundation-Sec-8B-Reasoning delivers on both fronts, achieving what the researchers call specialization without sacrificing generality.
Let's look at the specific general-purpose results, shown in Figure 4 from the paper. On Alpaca-Eval 2, which measures human evaluator preferences, Foundation-Sec-8B-Reasoning achieves 62.6%. This is an 89% relative improvement over Llama 3.1 8B Instruct, which only scored 33.1%. Human evaluators significantly prefer the reasoning model's outputs. On Big Bench Hard, testing complex reasoning, the model scores 69.9%. On GSM-8K grade school math, it reaches 82.3%. And on Human Eval code synthesis, it achieves 79.9%. What's particularly impressive are the multi-hop reasoning improvements from RL training. On 2 Wiki multi-hop QA, the model improved by 36.1 percentage points from SFT to the final RL model. On Hotpot QA, the improvement was even larger at 45.1 percentage points. These massive gains in multi-hop question answering demonstrate that RL training develops capabilities that go far beyond what SFT alone can achieve. The model learns to connect information across multiple sources and reason through complex chains of evidence, skills that are invaluable for security analysis.
Now, an absolutely critical evaluation: safety. The researchers used HarmBench with 400 representative adversarial prompts spanning hate speech, harassment, illegal activities, malware generation, and more. The pass rate represents the percentage of harmful prompts the model safely refused. Looking at Figure 5 from the paper, the results tell an interesting story. Llama 3.1.8b.instruct, the baseline, achieves only 62.75% pass rate. That's concerning for real-world deployment. Foundation-Sec-8B.instruct, the instruction-tuned version, jumps to 95%. Foundation-Sec-8B.Reasoning without any system prompt achieves 54.25%, lower because reasoning models are more susceptible to jailbreaks. However, with the recommended system prompt, it rises to 93%. And here's the key insight. With Llama Guard 0.3.8b protection added, the combined system achieves 98.25% pass rate. This demonstrates the defense-in-depth approach recommended for deployment. The three-layer architecture on screen shows this. Model safety as the first layer, system prompts as the second, and external guards like Llama Guard as the third. Together, they provide enterprise-grade safety for production environments.
To understand what each training stage contributes, the researchers conducted ablation studies comparing the SFT checkpoint with the final RL model. Table 7 from the paper shows these results. The SFT checkpoint provides the foundation. It has the reasoning structure and broad knowledge, but RL training adds significant improvements on reasoning-intensive tasks. For cybersecurity, CTIBench RCM improved by 5.8 percentage points from SFT to RL. CTIBench ATE improved even more at 9.7 percentage points. These gains directly impact practical security analysis capabilities. For general reasoning, the improvements are even dramatic. 2-wiki multi-hop QA jumped by 36.1 percentage points. Hotpot QA improved by 45.1 percentage points. These multi-hop reasoning tasks show the largest benefits from RL training. There is a minor trade-off. Human eval code synthesis decreased by 2.4 percentage points, but this small loss is far outweighed by the massive reasoning gains across all other tasks. The key takeaway is clear. RL is critical for reasoning-intensive tasks. SFT builds the foundation, but RL develops the extended reasoning capabilities that make the model truly effective for complex security analysis.
Let's really dig into why reinforcement learning matters so much for this model. Think of SFT as the runway and RL as the thrust. The runway gives you the foundation. You can't take off without it, but the thrust is what actually gets you airborne and to your destination. RL training provides three major benefits. First, extended reasoning capabilities. The model develops deeper analytical chains, going beyond patterns learned during SFT to reason through novel scenarios it hasn't seen before. Second, multi-hop question answering. Those massive improvements on 2-wiki multi-hop QA and hotpot QA show the model's enhanced ability to connect information across multiple sources. In security, this means correlating threat indicators from different reports, linking vulnerabilities to exploitation attempts, and building comprehensive attack timelines. Third, complex vulnerability analysis. The CTIBench ATE improvement of 9.7 percentage points represents significantly enhanced ability to extract and analyze threat information from security reports. Yes, there's a minor trade-off with a slight decrease in code synthesis, but for a security-focused model, the reasoning gains are far more valuable. The model develops capabilities that simply cannot be achieved through supervised learning alone. RL unlocks a new level of analytical power. So where can you actually use Foundation-Sec-8B-Reasoning? Let's look at 4 key applications. First, threat intelligence. Generate comprehensive threat reports with transparent reasoning chains. The model can analyze attack patterns, perform attribution analysis, and evaluate potential impact, all while showing its work. Second, vulnerability assessment. Prioritize vulnerabilities based on exploitability, impact, and context. The model understands cascading effects across systems, helping you focus on what matters most. Third, incident response. Get rapid analysis of security incidents with step-by-step reasoning.
The model can trace attack paths, perform root cause analysis, and recommend containment actions, crucial when every minute counts. Fourth, multi-hop security reasoning. Connect information across multiple security sources, correlate threat indicators, analyze kill chains, and build comprehensive threat actor profiles by synthesizing data from disparate reports. For deployment, the researchers recommend using the model with system prompts plus Llama Guard 3 8B protection. This achieves the 98.25% safety pass rate we discussed earlier. And best of all, the model is open source. The weights and documentation are publicly available for security researchers and practitioners to adapt for their specific use cases.
Let's wrap up with the key takeaways from this paper. First, Foundation-Sec-8B-Reasoning is the first open-source native reasoning model specifically designed for cybersecurity applications. This is a significant milestone for the security AI community. Second, the two-stage training approach, supervised fine-tuning followed by reinforcement learning with GRPO, proves highly effective for developing reasoning capabilities. Third, despite having only 8 billion parameters, it outperforms models 9 times larger on multiple cybersecurity benchmarks. Focused training methodology beats raw scale. Fourth, the model maintains strong general-purpose capabilities. Specialization doesn't mean sacrificing generality. You get both. Fifth, with defense in-depth protection using Llama Guard 3 8B, the model achieves 98.25% safety pass rate on adversarial prompts. It's ready for production deployment. The model is built on Llama 3.1 architecture with 8 billion parameters, and it's completely open source. You can find the paper on Archive, the model weights on GitHub, and the Hugging Face release. If you found this breakdown helpful, hit that like button and subscribe for more AI and security content. Thanks for watching, and I'll see you in the next video.